In this lesson, we're going to look at solving rational equations algebraically. Up till now, we've been using Desmos or other graphing software to graph both sides of a function and then find the point of intersection, or move everything to one side and then find the x-intercepts. But we want to be able to do this algebraically as well. But there are certain things we have to watch out for. So algebraically, what we can do is we can move everything to one side, as it says just above here. But another thing we can do is if it's a rational function and there's just one term, so to speak, on each side, then we can cross multiply. So I'm thinking of 4 over 3x minus 5. I'm thinking it as a single term. And if I've got one fraction, one unit, and if I think of the other side as a single term, then I can cross multiply. Remember, cross multiplying works if we have a fraction on each side, and I can turn this into a fraction easily enough. Cross multiply, we multiply the top of one side by the bottom of the other, and vice versa. Let's use a different color here. So we're multiplying like that. And it doesn't matter which side I put things on, so I could do the 4 times 1 on the left side, or I could put it on the right side, and then I have 4 times 3x minus 5. Again, really doesn't matter which side goes on what. But when I do that, then it makes it not a fraction anymore. It's just a polynomial that's a lot easier to work with. So then I can just carry out the simplifying. I get 4, and then of course when I use distributive law, I'm going to get 12x minus 20, and then I can carry on to solve this. Bring the 4 over to the other side. Actually, I don't want to bring the 4 over to the other side. I was thinking about rearranging for graphing, but that's not the way we normally do it, is it? I'll bring the 20 over to the left side, and so then I would have 24 plus equals 12x. And then I would divide each side by 12, and I'd end up with x equals 2. And you won't necessarily show the steps exactly the way I do, but you should get the same answer of x equals 2. So that is excellent. We can see that when we do that, it gives us the same answer. I've got the graph. I've sketched the graph of it over here. And when x equals 2, lo and behold, it does intercept the graph here at the point 2, 4. And so that's our point of intersection. That's our solution, right? So all I'm doing by showing the graph is showing, yeah, they do, whether we do it algebraically or whether we do it graphically, we should get the same answer. Okay, that was a really simple one, but the same principle holds even for more difficult looking ones. Like this one clearly looks a lot more difficult, but there's some similarities. We've got fraction equals fraction. So we can cross multiply. So if I use the same colors just to show, I'm going to multiply the top of one side. I need to put it in brackets, so x minus 5 times x squared minus 1. And then on the other side of the equal sign, I'll do, well, it doesn't matter. I like to put the smaller terms out front. So I'll put the 3, it's just a binomial, so smaller polynomial out front, and then put the trinomial after it. Just makes more sense when I go to multiply it later. So that's the cross multiplying, and we're proceeding exactly the same way. It's just that we have more calculations to do. It's going to be a bit harder to solve than the first example above. But if we expand this out, we do FOIL on the left-hand side, we'll get x cubed minus x minus 5x squared plus 5. And then on the right-hand side, we're going to have to multiply each of these terms by 3x, and then each of, let's use green, each of these terms by 2. So multiplying each term by each term in the other bracket. So I'm going to do 6 multiplications. And so I'll end up with 3x cubed minus 9x squared minus 12x. Then go back to do the 2, and I get plus 2x squared minus 6x minus 8. Yeah, I should try to write a little smaller because I see I'm encroaching on my space for part C. Anyway, then I can collect my like terms together. Maybe what I'll do, since noticed I did that, is I'll just write it underneath here. I really want to save my space because the other one's a bit longer too. So what was it? Plus 2x squared minus 6x minus 8. Okay, collect up the like terms. That's going to be our next step. So if I do that, I got x cubed minus 5x squared. I'm going to write them in order from highest exponent to lowest on the terms. Minus x plus 5. So really it was just rearranging as far as that side goes. And on the right side, I've only got the 1x cubed, but I do have a couple x squared, so it should become minus 7x squared. And I got a couple x's, so it becomes minus 18x minus 8. Okay, so now it's been simplified. Now let's bring everything to one side of the equation. Again, now it's a polynomial. Let's go back to what we've done when we're solving polynomials. So let's bring everything over to the right-hand side. So I'm going to subtract x cubed from each side. And so, if I subtract x cubed from each side, I'm left with 2x cubed. And if I bring that 5x squared to the other side, then I'm going to end up with minus 2x squared once I simplify the signs. And hopefully you can see how the pattern goes. We're just rearranging a bit and combining those ones, and we get minus 13. Okay, so now we've got an even simpler looking polynomial, and we learned a few lessons ago that we can solve this polynomial by using the factor theorem and some form of division to break it down into something that we can work with. So using the factor theorem, remember we focus on 13 and say, what are the factors of 13? Because if there's a factor of this entire polynomial, then 13, it has to also be a factor of 13. So really it's just 13 and 1. When we check positive 1, just to save us a little time, positive 1 doesn't work out. It doesn't go in evenly. We don't get a remainder of 0. But if we try negative 1, it turns out that one's going to work. Okay? So when I put negative 1 in for x in the above equation, I get 0. So I know that x plus 1 is a factor. And so that's part of my breaking it down. Now I have to divide. We've done this before, so maybe we'll go to the synthetic division. And I'll try to do it small to conserve space. And I'll get my coefficients. So I have 2, negative 2, negative 17, and negative 13. And do my synthetic division the way we've been doing it a bunch of times up to now. And I got a 0 remainder, which is good because that confirms that it's a factor. That means that if I were to, just jump down to the next step here, I got my first factor, which is x plus 1, and then if I multiply that by 2x squared minus 4x minus 13, then it's going to be equivalent to what I started with. 2x cubed minus 2x squared minus 17 minus 13. And then I go on from there, right? And so we need to try to find what we can use for factors of 2x squared minus 4x minus 13. So we've seen this before. We just carry on. Again, just to save a little bit of time, what's going to happen, whether you do trial and error or decomposition or whatever your preferred choice of factoring quadratics is, you're going to find that nothing seems to work. Okay? Sometimes that's the case. It doesn't mean that we can't solve it, though. If we check the discriminant, and let's do that over here, b squared minus 4ac, that's our discriminant, if you recall that. And if I put negative 4 squared minus 4 times 2 times negative 13. That's my ABC as far as A, A, B, C. Just to remind you, that's where I'm getting A, B, and C from. What I end up getting is 16 plus 6 times 13, which would be 78, I believe. Anyway, I'm pretty sure that's right, just doing it in my head, though. What I know for certain, though, is that I get a positive number. So remember, that just tells us that we've got 2 real roots. Oh, no, it's not. It's going to be 78. I just realized my mistake there. It's going to be 120. Just want to confirm that before I go any farther. Yeah, should have been 104 there. So 16 plus 104, that's what I thought, equals 120. Anyway, same result, positive value for the discriminant means that we should have 2 roots. So I haven't been able to factor it, but I know there's 2 roots. What that leaves us with, of course, is the quadratic formula. So the quadratic formula tells us, just as a reminder, let me write it over here as a reminder, because I want to use the other space, though, for my calculation. So negative b plus or minus the square root of b squared minus 4ac, which is, again, my discriminant, over 2a, right? So I'm going to use the same a, b, and c that I did just in my discriminant. So x is going to equal negative, b was negative 4, so negative 4, plus or minus b squared minus 4ac. I already calculated that. That's 120, so let's save ourselves a little bit of trouble here. Over 2a, which is 2 times 2. So I have 4 plus or minus the square root of 120 over 4. And putting that in the calculator, so I would do 4 plus the square root of 120. Again, I think I have to do it in this order, yes. And then divided by 4. So I got 3.74 as one of my solutions. Doing the same thing with the minus, right? So 4 minus the square root of 120. And divide that by 4. I got negative 1.74. So that's one solution. That's another solution. Don't forget we also had the solution from up above that x equals negative 1. We can't forget about that one. So back from when we did the factor theorem, way up here, let's find a color I haven't used yet. When I did the factor theorem, way up here, we found out that x plus 1 was a factor. We have to remember to list that as one of our possible solutions. And that's why I'm also writing that one in. So there's 3 solutions to this. We did it all algebraically. We could confirm it on Desmos, but now we know how to do it using just the math calculations. Okay, last example, same thing. Another one that looks more difficult. I mean, just going back to this for one more second, it was really the same approach as example A. It's just that example A was so simple, we were able to solve it using simple techniques. Example B, we had a cubic function we had to factor, and then we had non-integer roots, so we had to then use the quadratic formula. That made it more work, but it wasn't a different approach. It's always the same approach, and this one's the same approach again. If I cross multiply, then what I'm going to get is x times x squared plus 6, and I'm going to get x minus 2 times 2x squared minus 3x plus 5. And again, we can just expand this out. Okay, and then we can simplify again. Nothing to do on the left-hand side, but on the right-hand side I get 2x cubed minus 7x squared plus 11x minus 10, and then I can bring the x cubed plus 6x over to the left to have 0, so over to the right to have 0 on the left, and then I end up with x cubed minus 7x squared plus 5x minus 10. That's the polynomial that we need to solve for. So again, we're looking at the 10 here. This is what we have to consider if we try the factor theorem. And so the factors of 10 are going to be, could be plus or minus 1 times plus or minus 10, plus or minus 2 times plus or minus 5. So we actually have 8 different things we could try. I know how this one's going to work out, so I'll save us a little bit of time. If you tried plugging plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10 into this equation, not one of them works. In other words, you won't get 0 on any of them. None of those values are factors. So we can't use the factor theorem, we can't use synthetic or long division, but it's a cubic, and while there is such a thing as a cubic formula that's like the quadratic formula, it's much more complicated. We really don't want to take that route. So I'd say for our purposes in this case, if we know there's a solution, and there has to be a solution, the way I know that there's got to be a solution is that we're dealing with a cubic function, right? Picture a cubic function. It's got a positive leading coefficient. I can really picture this quite easily. I can't picture exactly what it looks like, of course, but I can definitely picture the basics. And the function is going to look like something like this. Maybe. I mean, it's possible that it might have more than one x-intercept. I've got one x-intercept here. But I do know certain things for sure. It's going to cross the x-axis at least once. Because it's cubic, because it's an odd degree. It's going to go from quad 3 to quadrant 1 for the end behavior, because it's got a positive leading coefficient. And it's also going to go through negative 10 as my y-axis, as my y-intercept. Because of the negative 10 on the end. So I know that much. However, it's possible that something else could be happening. It could look like this. It could go through negative 10 and go up and back down, and so it could be like that. So it could have up to 3 x-intercepts. I expect, though, that it's going to be, it could have 2 as well, right? It could just go, it could just touch in one place and turn away. So we could have 1, 2, or 3 x-intercepts. Anyway, all that we can't really tell with the information we have, so we're going to have to go to Desmos in this situation. Where was it? Y equals x cubed minus 7x squared plus 5x minus 10. Okay, so it's sort of a combination of what I was predicting. It does have a couple turning points on there. It definitely has the same end behavior. It definitely has the same y-intercept I was expecting, but it only has the one x-intercept, and it has whatever this action going on here is where we got the local max and the local min. Those are below the x-axis. But our one and only solution, which is all we're looking for, turns out to be 6.47 if I round to 2 decimal places. So that's how we can solve this one.